So we just went ahead and figured out the entropy change for a incompressible substance, right? So we went ahead and what we just did was we went ahead and took the TDS relationship in order to find the change in entropy, delta S, of an incompressible substance. Now let's go back and let's recall one of the TDS relationships in order to be able to compute the entropy change for an ideal gas. So again, I'm going to pull the Gibbs equation, which is TDS equals du plus PdV. Again, I'm going to divide through by temperature. And now what I'm going to do is use my ideal gas law, so you make some substitutions for internal energy for how to, the equation for how to compute the change in, or du in the change in internal energy for an ideal gas. And I'm also going to go ahead and use the ideal gas law to get this term, the pressure over temperature term, as a function of specific volume. So I'm going to go ahead and take du and substitute that into my TDS relationship, and go ahead and take the ideal gas law, substitute that into P over temperature, and I end up algebraically changing the form of the TDS relationship to be according to assumptions that I can make for the ideal gas law. So now what I can do is integrate this to get the change in entropy for an ideal gas. Now, if you come back and you look at this term ends up being a natural log term, and this term, as I integrate it, right, I'm going to go ahead and integrate all of these terms, and I get this equation below where I get the change in entropy is equal to the integral CV dt over temperature plus r natural log nu2 over nu1. Now, to take this further, I need to go ahead and make an approximation or make an assumption for my specific heats, whether they're constant or variable. So I get this is one form of being able to compute, being able to compute the change in entropy for an ideal gas. And I can also use the other TDS relationship and do much of the same substitutions. I'm not going to go through the algebra, but I'll go ahead and put this into the final form to find the entropy change of an ideal gas. So there's two equations for figuring out the entropy change of an ideal gas, depending on which TDS relationship we started with. This is equation, we'll call that equation number 2, and we'll call this one equation number 1. Now, in order to be able to evaluate these integrals, I need to make an assumption of the specific heats, whether they are constant or variable, much like we did in earlier chapters dealing with the internal energy and the enthalpy change of an ideal gas. The difference now is that entropy is a function of temperature and also pressure, not just a function of temperature like it is for an ideal gas trying to compute internal energy and enthalpy. So if I take those two equations, right, and I want to evaluate the integral, assuming constant specific heats, I get a natural log term. So I get CV, natural log T2 over T1, plus R, natural log nu2 over nu1, or, so that's for equation 1, right? If I go back to this and carry out the integral, assuming constant specific heats. And equation 2, which is the top part of this slide, ends up being Cp, natural log T2 over T1, minus R, natural log P2 over P1. Again, that's finding the entropy change of an ideal gas, assuming constant specific heats, yields two different equations. They give you the same answer, the only difference being using one or the other depending on the knowns in the problem. Now that is for constant specific heats. What if we have variable specific heats? Remember, variable specific heats means we assume and we account for the fact that the specific heat changes with temperature. How does that change, right? Well, in order to be able to quantify that, I'm going to go ahead and define a function. For a lack of better words, I call this S superscript 0, or the temperature-dependent portion of the entropy. Remember, the change in entropy for an ideal gas is a function of temperature and also pressure. So what we're going to do is I'm going to take this term for the second equation, right? This is only dealing with the second of the two equations. I'm going to take that term and I'm going to call it S superscript 0. So I integrate specific heat over a function of temperature. And so by using this definition, I can get that the change in the temperature-dependent portion of the entropy, S superscript 0, this change, so this delta S is equated to this whole equation. I'm going to take this part of the equation, I call it S superscript 0, so when I find the change in entropy, that's equal to basically integrating that portion, this portion of that equation, this portion right here. If I integrate that from T1 to T2, I can replace this portion of the equation with S superscript 0. So basically, the change in entropy for an ideal gas with variable specific heats would be regarded to as equal to the entropy, the temperature separating the equation into the temperature dependent portion of the equation and the pressure dependent portion. Right, so this part of the equation is this part. Basically what I'm doing is that I am accounting for the changing specific heat with temperature by going ahead and quantifying these two entropy values, taking the difference, and it is the same thing as if I am integrating the specific heat over dt, the specific heat over temperature time dt, right? It's as if I'm integrating this whole portion. What I'm doing is instead of carrying out that integral, I'm going to replace it with this variable S superscript 0. And these values are tabulated in the ideal gas table. So if you remember back in ideal gas tables, we went ahead to table A17 for air, for example, and table A18 for nitrogen. There's several tables for several different types of ideal gases. We used these tables back in earlier chapters to find enthalpy and internal energy as a function of temperature, right? And you may have noticed back when we were doing this that there's also this S superscript 0. Those values are for these parameters in this equation. So if I wanted to go ahead and find the entropy change for an ideal gas, assuming variable specific heats, I would go to the ideal gas table. I would go ahead and at the two temperatures take S superscript 02 minus S superscript 01. I'd find those values. I plug it into this equation at S2 and S1. I put it into that equation and then subtract R natural log P2 over P1, and that whole thing would give me the change in entropy for an ideal gas.